following on with the micro CPU250, and we're going to see how that interacts with stepper motors. If you have any questions, you can pop them in, we'll get them at the end.
Hello and welcome to today's webinar. Today we will look at using the micro CPU 250 with stepper motors. Let's take a look at our agenda for today. We are going to start with a quick review of the CPU 250. We will talk about stepper motors. We are going to talk about interfacing with stepper motors, whether you do it from a field bus or an industrial Ethernet, whether you do it strictly from I/O signals like step and direction. We are going to show you the steps involved in controlling motion from the CPU 250, and there will be demonstrations throughout, and we will finish with a Q&A session. Here is a quick look at some of the hardware features of the CPU 250. You can see them all covered here in detail. They are the hardware features and highlights for the CPU 250. It has all the prohibibles you are used to seeing in the micro series: a built-in Ethernet port, a couple of serial ports, a CAN port for remote I/O expansion, but it also has local I/O expansion using OCS I/O up to 7 modules worth, and it supports all the same protocols you will find in the micro series. From a CPU 250 standpoint, it also has an amazing complement of built-in I/O, and those are highlighted here. But today we are going to focus on the two high-speed DC outputs which are capable of stepper control. What is stepper motor? It is a type of brushless DC motor that is used for simple position applications. The way a stepper motor works is that a full motor rotation is always divided into a number of equal steps. It could be 200 steps per revolution, could be 400, or could be 1,000 of steps per revolution. Steppers are known for their ability to position without requiring any kind of encoder feedback, so they work well in open loop. Now, what are the advantages of stepper motors? Well, they have low cost. Again, they do work well in open loop type configuration. They are easy to use and have a great torque at 0 speed and at low speed, so you will not find them hunting around when they are resting, trying to hold position. They have a great torque when they are not moving. Now, when would you use stepper? Low cost applications, low speed applications, where you are moving from one point to another, maybe going from point A to point B to point C and back to point A. You get high continuous torque without the need of a gearbox. So how can you control a stepper motor from the CPU 250? Well, you have got some options. Plenty of stepper motors support CAN open. They have got it built right in, and CAN open is an option for the CPU 250. Another would be using Ethernet. You will find some stepper motors with Ethernet built in, and many of them support Modbus TCP, also supported by the CPU 250. But the most common interface you will find on the stepper motors is a pulse train style interface, which only requires I/O signals of a special type of control. And that is what we are going to be focused on today, using a pulse train interface to control a stepper motor. So how are we going to wire our CPU 250 to a stepper motor that supports a pulse train or step and direction style interface? Well, let's start with a step or clock signal, which is a signal that tells the motor how many steps to move that needs to come from one of the two high-speed outputs on the CPU 250. So that is either Q1 or Q2. Now, the stepper motor also requires a signal for direction clockwise or counterclockwise, and in some cases it will also need an enable signal. Now, those can be wired to any output on the CPU 250 because there are no high-speed requirements for those two signals. And then in addition to those three output signals, you are going to have a common and a 24-volt signal required as well. Now, we need to talk about what is called a trapezoidal move profile. This is the type of move profile that the stepper motor is going to execute. What does it consist of? Well, the stepper motor is going to see a pulse train that will cause it to start accelerating from a starting frequency up to a running frequency. It will take a certain amount of time or a certain number of pulses to accelerate. Then it will get up to the running frequency where it will stay for a certain number of pulses. Then as it approaches the destination, it will start decelerating back down to its starting frequency and then stop at the destination. So by specifying the parameters in the table on the left, the CPU250 is able to put out a pulse train which will cause the stepper to execute the trapezoidal move profile on the right. Now let's give an example with some numbers. Let's say we need to move a total of 8,000 pulses. Maybe that represents 40 revolutions. Maybe it represents 5 revolutions of the motor. But we want to move 8,000 pulses. And we know we need to start with acceleration and end with deceleration. And let's say we want 800 pulses of acceleration and 800 pulses of deceleration. Well, that means we need to run at 6,400 pulses to get a total of 8,000 pulses. Now, what velocity do we want to run at? What number of pulses per second do we want to run at? Let's say that our max speed we want to run at for the move is 2,400 pulses per second, and we are going to start with a velocity of 800 pulses per second. That means during acceleration we are going to have an average of 1,600 pulses per second, as you can see there on the chart. So how do we get these numbers to the CPU 250? So those pulse trains can be generated. We do that by putting those numbers in the appropriate I/O registers that are allocated for the stepper function. And you can see in the chart on the left, the next to the last column shows the I/O references for stepper number 1, and if we're using stepper number 2, the I/O references are shown in the last column. So we load appropriate values in the appropriate I/O registers to specify the move, and then kick off the move by returning on either Q1 for stepper number 1 or Q2 for stepper number 2. And we have also got some feedback bits we can use to make sure everything's working as it should. Now here is a flowchart we have created that shows how the I/O should be changing as the move progresses. For our demonstration, let's start by taking a look at our logic in Cscape. The first step in our logic program is we need to specify the move. So we need to specify the start frequency and the run frequency. These are both in pulses per second. So we are going to start at 1,000 pulses per second at the beginning of acceleration and the end of deceleration. And our full speed is going to be 10,000 pulses per second. And then we also have to specify how many pulses we want to accelerate, how many pulses we want to decelerate, and in between how many pulses we are going to be running at full speed. And all these variables we have created are tied to the appropriate I/O registers in the program variable window. So let's go to the program variable window and see that these variables are all tied to the appropriate register as per the table from our slides and also as per the user's manual. So we have prepared for the move by loading in these values. Next we are going to go through a simple process. First we need to kick off the move by turning on Q1, and this particular variable is tied to Q1 in our case. We are just turning it on through the slide switch that is in our I/O stimulator. Next we need to monitor the feedback bit to see the motor has started moving. So our start move bit is on. We have turned it on. We wait for our move ready bit to turn off. That is the I30 bit. We are talking about stepper number 1. When that happens, we are creating a state in our program called move in progress. So that is how we know that the move has started, because this feedback bit has turned off. Now once our move is in progress, when that feedback bit turns back on again, we know that our move is complete. So we can go ahead and say the move is complete. That is a new state. We turn off the move in progress state. We turn off the start move command at the beginning, and then we will be ready for another move to execute, again by kicking it off again. In our case, by turning on this push button and doing the whole sequence over again. Let's take a look at it on the bench. To demonstrate our move, we are going to stimulate the press of a momentary push button by sliding switch number 1 on and off, and that is kicking off the move, and we are just repeating it here with multiple presses of the button. And of course, you can set up the sequence with multiple moves in different positions. We can do all that just by adding logic to our CPU250. That concludes our webinar for today. Thank you so much for listening, and the Q&A session will begin shortly.
Okay, so we will be carrying on to CPU 250 next week again, which will be with the use of variable frequency drives. So if that is of interest to you, then the registration link is there. It'll be the same time as always. Other than that, I don't see any questions in on the topic today. Thank you all for joining us. We hope to see you next time.